title of the tutorial class is Green's Theorem and Consequences. I will repeat the Green's Theorem that I provided last week as a consequence of Stokes' Theorem. We derived the Green's Theorem from Stokes' Theorem. Stokes' Theorem is easily stated. And from there, when we move to two dimensions, when we constrain our domain to a plane, we're going to arrive at a very important result. And that result is so important, it is called Stokes' Theorem. Stokes derived that theorem on its own without any reference. Sorry, Green derived that without any reference to Stokes. So, and it's a very important result. But we will put the two together because they are essentially the same result. One applies to the three-dimensional Euclidean point space. The other one applies to the plane. But there are two theorems that are very important, even though essentially they are the same thing. But we are going to treat them as if they are not. But we will just move from Stokes' theorem to deriving Green's theorem. And then we're going to look at some consequences. Last week, I did that same thing. I derived Stokes' theorem, Green's theorem from Stokes' theorem, but the notes there were in error. There are mistakes in that note. And because there are mistakes in that note, I have done the derivation again here in a correct way. So I will start with that. After that, I will remind us again our journey in the integral region, where we are moving from one kind of integral to the other. I hope by now everybody in this class knows that an integral is not the area under a curve necessarily. An integral is far more general, a concept than that. And you need to grow in your understanding of concepts to be able to make the best use of these issues. So we will look at what an integral is, and we'll look at the different kinds of integrals. And these are not just names, they mean specific things. And it is good for you to understand what they mean. And the exam you are going to take is going to test your understanding. And your understanding is going to improve by your working things out. Memorization may work to some extent, but memorization is not as important as understanding. If you understand and you practice a lot, you retain the things in your memory easily. That is my own experience. I don't know about yours. And I want the class to remember that every student in this course, just like in virtually all my courses, every student decides how good they want to perform. If you want an A in this course, it is yours. If you want a B, it is yours. If you want a C, it's yours. If you want to fail, it's yours. There are specific things, there are consequences, there are causes and effects. There are things you will do if you want an A. Come to class on time, take the classes seriously, practice the examples that you are given, go to do your self-testing on the website, ask questions. If you do all of that, I don't see any reason why you cannot get an A. If the entire class does that, I don't see, there is no limitation for any lecturer to give A to everybody in the class. That's what they deserve. Just as there is also no limitation to give F to everybody in the class, if that's what they want, and that's what they deserve. So what you get is going to be what you choose to get. As for me, I will do my part. I'm going to help you as much as I can. I'm not going to be lazy. I'm going to work hard. And if I make a mistake, I will acknowledge it. Like I made a mistake last week. I gave you an erroneous formula, and I've corrected it. And today, you are going to see examples that I've worked out. I went all out to work every step of these examples because I'm going to use them as a tutorial for you to see how other examples can be worked out. And it is also to prepare you for your test. So if you don't take that seriously, and you see the same things in the exam and you fail it, then I don't know who you will blame, whether it's me or something, or your stars, or the witch from your village. You blame anybody you like. All I know is that if you want to get a good grade, it is your choice. So Green's theorem can be viewed as a two-dimensional version of the 3D Stokes theorem. If we have two scalar fields, these are independent functions. They don't necessarily have anything to do with each other. are defined over the Euclidean point space. Instead of being a function of instead of each being a function of 3 variables, they are now functions of x and y, or x1 and x2. You know, we use those things interchangeably. When I want to use the numerized coordinates, I say x1, x2, x3. If I want to use the regular familiar one, x, y, z. So I keep oscillating between those two from time to time. So given two scalar fields, functions defined over a two-dimensional Euclidean space, we can form the vector Vx, which is equal to P1, E1, P2, E2. And we can now take the curl of V. The curl is this determinant. It's not a matrix, the way I did it last time. It's a determinant. And if you open this determinant, the E1 will give you, E1 doesn't give you anything useful, because when you take E1, you are 0 here, and you are differentiating P2 with respect to X3. Since P2 is not a function of X3, everything there is 0. If you take E2 also, you are differentiating P. If you take E2, you are differentiating P1 with respect to X3, and you are multiplying, you are operating the operator on 0. So everything vanishes except the components of E3. And these are the components that survive that curl operation. So that is 1. I got that wrongly last week. So we will correct and repost the lectures there. We have not yet done so, but it is good for you to notice that this is a correct thing. Now, from Stokes' theorem, the integral of the vector V taking over the closed path is equal to the curl of V taking over the surface. The difference now is that the surface we are dealing with is just a plane. Because the surface is a plane, the normal to that surface is a constant vector E3. E3 is constant, and that is the normal to the plane. In the generalized Stokes theorem, the normal to the plane is not constant. So that one feature of the Green's theorem is that the normal to the plane is constant. So you will see that the vector part of the vectors will just vanish, and there will be no need for a vector equation. Green's theorem is a scalar formula. It's a scalar formula. Everything there will be scalars. And it is coming from the fact that the element of surface is just a scalar multiplying a constant vector. So you can see that the S here is equal to the A E3. The S is equal to the A E3. So we are writing the Stokes theorem again. We now have, instead of Vx, we have P1 E1 plus P2 E2, as we have found out, dot the gamma, where gamma is the position vector along that path. It is not just ordinary position vector, it is the position vector that is compelled to stay on that path. That is the meaning of a line integral. The variable of integration is compelled to stay on that path. So if you perform a line integral and you do not at any point in time impose that restriction, you have not performed the line integral. To do a line integral is the compelling the differential of the integration to stay along the path. If it strays from the path, you are no longer performing a line integral. Okay, so that is the left-hand side. The right-hand side is the dot product of the curl of V dot ds. We've already found out that the curl of V is the P1, the X2, minus the P2, the X1. We take a negative of that because the negative sign appears in what we obtained before, and that is and they are both in the direction of E3, and we are taking the dot product of that with the A plus E3. Remember, the A is the scalar element of area, and E3 is the vector direction of, is the vector unit, is the unit vector direction of that scalar area, and that is what gives us the S, as you can see. And by the time we take that dot product, we have on the right-hand side minus the surface integral of the P, the X2, the P1, the X2, the P2, the X1, the A. The last expression there is no longer a surface integral. It's just an ordinary double integral. And the surface we're showing there is now just the domain of integration. So we have moved from a surface integral of Stokes to a simple double integral. So all you are going to do on the right-hand side is constrain the domain to stay within the region. And that region is a plane. Whereas on the left-hand side, you are constraining the unit vector, the position vector, to stay along the line. And the examples I will show, they are simple, but we see how we force the integration to obey those constraints. And I will also write a code for you using a computer program to get it. What that tells you is it tells you that when it's very simple, you can do it manually. When it's very tough, you don't need to worry. You can just substitute the values in the program and you get the answer almost immediately. So, and the problem you are going to have is to specify the boundary conditions correctly. So, specifying the boundary conditions will be the real heavy lifting. And that is why in your final exam, I am going to test your boundary conditions much more strongly than I test whether you can integrate. But I am not saying that you didn't know how to integrate. In fact, it is the people that can integrate that will pass well, because it is when you integrate correctly that you can see the answer. And that is the answer after you have practiced several times, helps you to remember how the things here actually work. So it's not a trivial matter to integrate, but when the thing becomes difficult, I expect you to use computers to integrate, because that is what you are going to do in real life. In real life, you are not just going to be doing the drudgery of integrating yourself and integrating. Cartesian position vector in a plane. Because we are going to get, gamma will be a position vector that is lying along the path. We will just say, well, on a plane, if you take x and y coordinates of a point along the path, the position vector of that thing will be xi plus yj. Since you are staying on the plane, we're assuming now that the origin is also on the plane. Makes sense to assume that because you are not leaving the plane. There's no reason to go and put an origin in some other place. Now, the next thing we need to do, because if you look at this formula here on page 3, if you look at the formula here, you see that the thing here is the differential of the position vector. So that is the differential of the position vector. So you have to be careful that you understand how to get the differential of the position vector. So on this page now, if you have your position vector gamma is xi plus yj, how do you get the differential? You notice that when we are on Cartesian coordinates, the differential, the position vector is a linear function. It is xi plus yj. I is constant, j is constant. The only thing varying is either x or y. That's the only variable there. So it's linear. It's linear. And so if you take the differential, it is idiot proof. And this can lull you into complacency that if you go to any thing, well, you just take the differential, you just put d in front of the coefficients. That cannot be further from the truth. That is not correct. In fact, there is a formula that will always work to move from a value to the differential. And that is what you should be using. Even in the simple case like this, it will also work. I will come to that shortly. So we have that d gamma is the xi plus the yj. I hope you can see that and you agree with that. Or the x1 e1 plus the x2 e2. If you are using e1 and e2 and x1 and x2 to represent the coordinates and then the unit vectors along the coordinates respectively. Since the Cartesian the position vectors are constants in magnitude, so there's an error again. It is not the Cartesian position vectors, it is the Cartesian coordinate unit vectors. Coordinate unit. So it is the Cartesian coordinate unit vectors that are constants in magnitude and direction. They are constants in magnitude and the magnitudes, and they are also constants. If I say I has a magnitude of 1 and has a specific direction that does not change throughout your analysis. J also has a magnitude of 1, it's perpendicular to I, and it is fixed throughout. That kind of situation only happens on Cartesian coordinates. In virtually any other coordinate system you are going to use, the position, the coordinate vectors are not necessarily constant. And that causes a lot of problems. So you must be very, very careful on that. I'm sorry, I am just, maybe I woke on the wrong side of my bed this morning. I'm saying wrong things everywhere. I saw that I missed an I in that place, and I want to correct the thing right away. So there, okay, so if we write the functions P1, X1, the P1, which is the function of X1, X2, in the direction of E1, we can write it as M of XYI, and the other one, P2, X1, X2, E2, as N of XYJ. Those are more familiar ways of representing them that you find in your textbooks. So quiz, I want you to write the position vector for spherical as well as cylindrical coordinates, and then try to see whether you can obtain the differentials the way we have obtained the differentials here. And I'll wait for you in the chat room. You'll see now that I have written the position vector in Cartesian and I've obtained the differential. You write the position vector in spherical or cylindrical, and let us see the differential. Because to move from one to the other is very simple in Cartesian. It is not simple in the other, but it's doable. You can get them, and you're not just cramming. You can always do them. Take the step. I want to see whether I've already taught you this before. If you are missing it now, because those are kinds of questions I can ask you in an exam, and I want you to get the answer correctly. So I want us to be sure that we know what we are talking about. Okay. Cylindrical, yes. Write the position vector in the cylindrical and the position vector in spherical, and then show me the differentials. Like you have here, okay, cylindrical R cos theta plus R sin theta. Okay, that I'm seeing R plus Z is Z. Please, when you are talking of position vector, okay. Then after you have done that, I want you to write the differential. Write the position vector, write the differential. And well, I just want to see whether how many people know it. Write the position vector in spherical too, and write the differential. Emmanuel Ashize, that would be two-dimensional. RER would be two-dimensional. Spherical, Olajide Bitoye, what you have written is Cartesian. Okay, R1, that cos phi E1 cos cylindrical. Oluwatobi, you are correct. The cylindrical is RER cos Z is Z. But we are still, I'm yet to see anybody with spherical as well as showing me how the differential will look like. I've not seen anybody getting this spherical. So if you find it difficult to understand this, you have to go back to a spherical rho sin theta ER plus rho cos theta EZ. Spherical. Josiah Adeshola, you are wrong. Habib spherical is E rho. Habib, you are close. You are not correct still. Cylindrical DR is equal to D RER plus DZ. Monioluwa. Yeah, I know you are right but you are waiting for the differential. Sulaiman Bolaji, what are you writing? You just because I'm asking several questions. You just dumping something that doesn't tell me what you are doing. Monioluwa, spherical R is equal to rho E rho. That is correct, but we are still waiting for the differential. So we are waiting for the differential. Remember that here I wrote the position vector, then I wrote its differential. Mojoluwa, you are correct in writing it something, but you have not written the differential. Oluwafemi, rho cos something, rho cos phi cos theta. Well, you have not IJK. When you are writing IJK, that is not a spherical. You are still starting from the differential. Okay, Josiah Adeshola, the cylindrical differential that Josiah is written is wrong. You see, that is the thing. That is the irony. The way the differential looks is not the way when you are in a nonlinear coordinate system, the differential looks completely can look completely differently from the way the position vector itself looks. That is the thing. Josiah, that is the thing you are. So just take note when you get the right thing, Josiah, so that you will not make a mistake that you are making right now in an exam. Okay? Oluwa to be spherical, R is equal to rho E rho. You got that. We are waiting for the differential. Now, I think the spherical is R is equal to rho E rho. The cylindrical is R is equal to RER plus ZEZ. So forget about that one. I want you now, everybody that is going to give an answer, show me that you understand how to get the differential. Now, how does the differential look like? I want you to see that the differential is a little bit more difficult to get, but you need to get it because I'm expecting you to know how to get the differential in any coordinate system. Even in the coordinate system I have not yet introduced, because I show you how. Okay, let's leave that. You are nobody, not one person in the entire class has gotten the differential from the other coordinate systems. The R, which unlike you are not telling me what you are doing. Is that spherical or cylindrical? So I don't know how to interpret what you're saying. And what is the meaning of vector theta? Are you talking of E theta? The R the theta, vector theta, R sine theta, d rho, vector rho. Well, I can see that the class didn't think this. I taught it already, but you either have forgotten because you need to keep coming up with this knowledge all the time. Like our time is fast spent, so I have to move on. I have to move on to other things. So just know that you didn't get this right, and some of you know how to get the position vector in cylindrical and spherical, but you do not know how to obtain the differentials. But for this course, for this class, we are just looking at the differentials in the Cartesian, which we are okay with. What happens is that, so with that, once you substitute that, you now find out that you can write the Green's theorem like integral over gamma of P the x1, P1 the x1, P2 the x2, and it is equal to minus integral over the surface of the P1 the x2, the P2 the x1, the A. So that is the Green's theorem. Now, this is how you find the position vector and their differentials in curvilinear coordinates. The first step is that you must get the expression for the position vector correctly. You see, this is a general formula. For instance, if it is cylindrical, it will be RER plus ZEZ. If it is spherical, it will simply be rho E rho. That's all that it will be, only a single term. Now, this functional form, but whatever you do, it will be like in the spherical, it is a function of rho, theta, and phi, because even though rho is appearing explicitly, theta and phi are implicit in the vector itself, because the vector itself is not constant. It is varying with theta and phi. So rho, theta, and phi are implicitly present in the value of the position vector. Now, how do you get the differential? To get the differential, you go to multivariable calculus and you remember that when you have a function of 3 variables, The total differential is the differentiation with respect to the first one, the row, the differentiation with respect to the second one plus the theta, and then plus the differential with respect to the third one plus the phi. The trick now is that what is the R, the row? The R, the row is the first component, is the first coordinate vector E row. What is the R, the theta? The R theta is the second vector E theta. And what is the R the phi? The R the phi is the third vector E phi. Go and look at the notes, the last two lecture notes. These things are there. And that is how, so you can see that even though your position vector can have one term or two terms, the differential vector has three terms always. So, and this is why it is so. And I cannot emphasize this thing enough because I am going to ask you this in the exam. So do not make any mistake about it. I can ask 5 questions about this in the exam. So it is important, very, very important. Okay, so go back again. We remember talking about simple integral, area integral, volume integral, line integral, surface integral, and we are doing integral theorems now. So if we go back to our Cartesian thing, using between M and N, this is how the Green's integral theorem now looks like. The surface integral now becomes an ordinary double integral in the XY plane. We only need to correctly specify the defining boundary domains. The defining boundary domains are important. That's why I've been emphasizing on it, and I will be asking such things in the exam. The left-hand side integral remains a path integral. Even though you are seeing the integral with respect to the x, but it is significant that the integral has that gamma and that's O at the integral. It's not just an ordinary integral, it is a path or a contour or a line integral. And you must still connect the constraining relationship. The real issue about a line integral is that there is a constraining issue that forces that integration to take place along the path to obtain correct results. And we are going to use a very simple example to show how this is done and at what point you implement that constraining relationship. If you do not implement a constraining relationship, you are not doing a line integral.